Hi, Professor Dave again. Let's discuss electric field. We live in an age where we take electricity for granted. Just plug into the wall and you can power any device you want. But what's in there? What is electricity made of? The discovery of a variety of phenomena over several centuries eventually led to our mastery of this incredible power. So let's learn about it now. First, we noticed that there was such a thing as electric charge. The easiest demonstration of this involves rubbing a balloon on your hair and seeing how the balloon will then attract your hair by some mysterious force.
Two balloons that have been rubbed on your hair will strangely push each other away. This occurs because of electric charge, which is displaced by the rubbing together of these materials. The hair becomes positively charged and the balloons become negatively charged, which is terminology developed by Benjamin Franklin. Opposite charges will attract one another, which is why your hair sticks to the balloons, and like charge repels, which is why the two balloons push each other away. This property of electric charge is carried by certain subatomic particles. The most common of these are protons, which are positively charged, and electrons, which are negatively charged. Along with neutrons, these make up all the atoms in the universe. For more about atoms, check out my general chemistry course.
As it happens, electrons, which are the essence of electricity, are easily transferable, and it is the transfer of electrons. In this case, from your hair to the balloon, that generates electric charge in previously neutral material. Each electron carries with a fundamental charge, which is 1.6 times 10 to the power of negative 19 coulomb. This is magnitude is negative for the electron and positive for the proton. All substances will therefore have a charge that is some multiple of this amount. That is to say, that the charge is quantized.
We can categorize substances by their ability to transfer electric charge. A substance that can easily transfer electric charge is a conductor. One that can't is an insulator. Opposite charges attract one another because of the electric forces. This is outlined in Coulomb's law, which stated the magnitude of the electric force between two objects is equal to the Coulomb's constant times the charge on one object times the charge on the other divided by the square of the distance between them.
This is essentially identical to Newton's law of universal gravitation. The only difference being that the electric force can be attractive or repulsive. Depending on the gravity is always attractive. Also, it is interesting to note that Coulomb's constant is 20 orders of magnitude greater than the gravitational constant. And illustrating the discrepancy in the strength of the two forces. This law also tells us that the electric charge between two forces is increased. Also, as the charge increases and decreases when the distance of the two objects decrease. If more than two charges are present, vector addition must be done to find out the net force upon any particle in the system.
Just as the gravitational field is what allows the gravitational force to propagate, it is an electric field that allows the electric force to propagate. However, as we said, the electric force is much stronger than gravity. This is evidenced by the fact that the repulsion between particles in your feet and particles in the ground is more than strong enough to keep you from plummeting towards the center of the earth. We can also use a cheap refrigerator magnet to keep a pieces of paper on the fridge against the gravitational pull of the entire planet. Any charged object will manifest an electric field around itself, and if another charged object enters this field, interaction will occur. The strength of an electric field generated by a point charge is equal to the Coulomb constant times the charge of the object producing the field divided by the square of the distance between this object and whatever it is acting on.
One way we depict electric fields is by drawing electric field lines, which generally points toward negative charges and away from positive charges and do not cross. These don't really exist, but they are a convenient way to analyze the direction of a field at any point in space. like the fields produced by these two oppositely charged particles, which we can call an electric dipole. The more densely packed the field lines are in a particular region, the greater the strength of the field. Okay, dah.